Welcome to the wonderful world of physics. This is chapter 19 on the second law of thermodynamics, and it's the final chapter in our unit on thermodynamics. In this video, I'm going to cover three sections, 19.1, which is rather brief, and then 19.2 and 19.3. Section 19.1, a very brief chapter, discusses the notion of reversibility and irreversibility. And what I want to talk about is the idea that nature generally goes from state of order to disorder. So let's look at this picture at the top. Here we have hot water and cold water. There's order to that. And if I wanted hot water for a cup of coffee, I know to go to the cup on the left. If I want cold water for a nice cold drink, I know to go to the cup on the right. Now, if I mix those two cups together, I pour them both into a larger cup. Initially, there'll be the hot water on one side and the cold water on the other side, but they will mix and they'll come to a medium, an equilibrium temperature. Conservation of energy says that the hot water molecules, they will bump into the cold water molecules, so the fast molecules bumping into the slow molecules. And the fast molecules will lose kinetic energy, the slow molecules will gain kinetic energy, and those changes will keep happening until there's an equilibrium temperature. That is going from order to disorder, so our water is no longer ordered. Now, if we recorded that on a video and we could see what the temperatures were in the water, and then play it backwards, it wouldn't make any sense. Imagine we're watching this video backwards and we see from this equilibrium temperature, hot water organized to one side and cold water organized to another side. And that would be going from disorder to order, and nature doesn't spontaneously do that. It would not violate conservation of energy to do that, but it is unlikely to go from disorder to order. Another example is dice. You can have the dice all lined up like they are on the left and they're all showing the same side, and you scramble them, and chances are they will go to a more disordered state. Now, there are many possible disordered states. You can see the one on the top left, it's showing us a 4, it could be showing us a 6, it could be showing us a 2. The one in the middle top could be showing us a 6 as it is, or a 4, a 3, or a 2. And so there's so many different possible other states, these disordered states, but there's only one state like the one on the left. So chances are it's not going to go back to the order that is on the left. And this is the notion of irreversibility. Many processes that happen in nature are irreversible, meaning it'll go from order to disorder, but going from disorder to order won't happen, or at least it is highly improbable for it to happen. It's irreversible. You can also see the picture down below. You have a mug, and if you drop the mug and it shatters and it goes into more disorder, and if you drop it on the ground, chances are it will not go back ordered, meaning it will not reassemble itself into the more ordered state. It is highly more likely to go disordered. So the breaking of the mug is an irreversible process. It will not reverse and go from disorder to order. Now, it will not spontaneously do that. Certainly we can step in and do things such as we can take the shattered pieces of the mug and we can glue it back together. We can take the dice and carefully arrange them back in order. We can take this lukewarm water, separate it into two cups, put one in the microwave and the other in the refrigerator, but spontaneously that separation of going into hot and cold, that reorganizing of the dice, the reorganizing, the putting back together the mug, that doesn't happen. So all those things that the reverse processes can obey conservation of energy, but they will not occur because it's way too improbable. Section 19.2, the second law of thermodynamics. And I want to talk about heat engines, an invention from several centuries ago. What they recognized, going back to the 1700s, is that it's easy to get thermal energy from mechanical energy. And a quick way to do this is you rub your hands together vigorously and you can create heat. The friction gives you that heat. So we can get thermal energy from mechanical energy. But the question in the 1700s was, can we do the reverse? Can we get mechanical energy from thermal energy? Can we take heat and somehow get useful work out of it? And the answer is yes. So there was this idea that was invented called a heat engine. A heat engine extracts internal energy from a system. So internal energy, think of that as heat, and it converts it to useful work. And this brings us to the second law of thermodynamics. Now, what you'll see is that the second law of thermodynamics has a variety of statements. It's stated different way by different scientists along the way. And when you, at first glance, read those different statements, they all seem very different. But they're not called the second law and then the third law and the fourth law because as we learned more about thermodynamics, it was realized that all these statements are talking about the same general principle. So here is one statement. It's called the Kelvin-Planck statement of the second law of thermodynamics. It is impossible to convert thermal energy entirely to work. And the key word is entirely to work. I'll read you the book. The textbook gives it a bit lengthier. It says, it is impossible to construct a heat engine operating in a cycle that extracts heat from a reservoir and delivers an equal amount of work. But my statement, as you see on the screen, is a bit more concise. It is impossible to convert thermal energy entirely to work. Here is a thermodynamic diagram of a heat engine. And as we go on through this lesson, I'm going to relate this to an automobile engine. And later we'll see how it's very similar to a refrigerator and an air conditioner and a heat pump. So here is how generally a heat engine works. You have what's called a high temperature reservoir right here. This is somewhere where in some way there is a high temperature. And heat is going to be extracted from it. So there's Q sub H, and all of our Q's and W's are going to be positive, unlike in previous chapters where Q specifically referred to the heat put into a system. For purposes of these diagrams and in this chapter, all of our Q's and W's are going to be positive. So Q sub H refers to the amount of heat that is extracted from the high temperature reservoir. And then that amount of heat, which is measured in joules, gets put by the engine. It gets turned into work. Now, right now, I'm not going into the ins and outs and the mechanics and the nuances of how it turns it into work, but the general idea of a heat engine is that somehow it turns it into work. The second law of thermodynamics says as many joules as got extracted in the form of heat cannot all be made into work. Some of it gets turned into something else. So a little bit of heat, think of this as exhaust, is dumped into a lower temperature region. Often that's the environment. So if you think with an automobile engine, without getting into how exactly the mechanics of how the engine works, in general, we have an amount of energy in the hot engine, and a lot of it gets turned into useful work. That's making your car move down the road. But some of that heat gets dumped into the environment as exhaust, into the low temperature reservoir. Conservation of energy says that the amount of heat extracted, Q sub H, is equal to W plus the amount of heat that is wasted away, that's exhausted, Q sub C. Let me use this idea of a heat engine to show you how a steam turbine works. Now, a steam turbine is actually the basis of, even though it's a centuries-old invention, it's the basis of how electric power is produced today. So here we have a steam turbine. It's a wheel that turns, and we have a pipe leading to it. And on the left is hot steam. So first we need to get the steam hot, and practically today this is done by burning coal. It can also be done by nuclear power, but however it's made hot, we have hot steam. That's our hot temperature or high temperature reservoir. And so it is at some temperature. I'll call it T sub H for T sub hot. And so on the left, we have steam that is high temperature, high pressure. On the other side of the turbine is a cooler area. And so the steam that's going to be on the other side is going to be lower temperature, lower pressure. So its temperature is T sub C for T sub cold. Now, if you've got high pressure on one side, low pressure on the other side, that's going to get this turbine to turn. And the bigger the difference in the temperature and pressure between the left side and the right side, the faster the turbine is going to turn. So the higher the temperature versus the colder the temperature on the right, we're going to get a better effect. And it only works if you have some bit of a higher temperature on the left than the right, because if they're the same temperature, they're going to be the same pressure, and this thing isn't going to move. So here you see that this difference in temperature is giving us mechanical work. We can talk about the efficiency of the engine. The efficiency is given by, before I give you the equation, well, you can see it right there, but look what I've written in the green. Efficiency is a ratio. It's something between 0 and 1, and you can just in general think of efficiency always as, in the numerator, the thing that you want, the thing you're striving for. And in this case, it's mechanical work. That's the whole point of our steam engine. We want work, so that's so many joules of work, divided by what you supply, what you pay for, what you invest. And so in this case, we are supplying heat from the high temperature reservoir, the heat that's being extracted. So in the case of a steam turbine, of a heat engine, the efficiency is the work divided by the heat extracted from the high temperature reservoir, W divided by Q sub H. Another mathematical expression of that, we can take E equals W over Q sub H. Recognize from conservation of energy in the numerator that work is Q sub H minus Q sub C. And then we have, when we simplify this fraction, 1 minus Q sub C over Q sub H. Now, this expression is useful if we don't know the work, but we do happen to know how much energy is dumped into the cold reservoir versus how much was extracted. But there's another highly usefulness to this expression, where my pointer is, and we'll get to that very soon. Now, W is defined as work done by the engine. In a previous chapter, in chapter 18, W was defined as the work done to the system. But this is a totally different work. It's still work, it's still measured in joules, but we're defining it differently. Here's a schematic diagram of an electric power plant. So we start with, we have water, and we need a heat source. And again, that's going to come from burning coal, nuclear power, something like that. But it boils the water, it makes it very, very hot steam. So it says here, the water boils to steam, and we've got this high temperature, and notice here's the high temperature, the low temperature, here it calls them T1 and T2, but that difference in temperature is going to yield a difference in pressure, and it's going to turn the steam turbine. Now in turning the turbine, we have a generator here, which is going to produce electricity, and later on this semester, we will talk about how the turning of a turbine can produce electricity. So hold on for a few chapters, we'll get to that. But now we have the colder temperature, so it goes here, and then there's a condenser, so something that actually cools it down. So it helps to produce a temperature differential, high temperature here and a low temperature here. So it says here goes the waste Q sub C out, and then the water continues in the cycle, and it returns to the boiler, and then it can be heated up again and sent through. A heat engine that works at maximum efficiency is called a Carnot engine or an ideal engine. So the idea here is that by the laws of physics, by the laws of thermodynamics, there is a maximum possible allowed in the universe efficiency for any heat engine, and it's this. Now, I told you a couple of pages ago that it was a useful expression for efficiency. It was 1 minus QC over QH. And now I'm showing you, it makes it easy to relate to this equation. If you switch the Q's out for T's for temperature, then that's the equation for the Carnot or the maximum efficiency of an ideal engine. The book goes into a derivation. It's more than simply changing the Q's into T's, but if you're interested, you can read in the book in section 19.2 for that derivation. But for this course, it's enough just to give you this equation. The maximum possible efficiency a heat engine can have is 1 minus the cold temperature minus the hot temperature, meaning the temperature of the cold temperature reservoir and the temperature of the hot temperature reservoir. You need to be careful. You need to use the Kelvin scale. If you plug in Celsius, you're not getting the true ratio of the temperatures. Now, usually, T sub C is the temperature of the environment. In the earlier picture that I showed you, the schematic of the steam turbine, it was actually the temperature that the condenser was making it. TH is as high as you can make it. So as the temperature, the hot temperature reservoir, as that temperature goes up, efficiency goes up. Let's do an example in the book that shows this. Example 19.1. It says a Carnot engine, and that just means an ideal, you could say a perfect engine, extracts 240 joules from its hot reservoir during each cycle and rejects 100 joules to the environment at 15 degrees Celsius. How much work does the engine do in one cycle? What is its efficiency? What is the temperature of the hot reservoir? Here I've written out the given information. So Q sub H, it's pulling out 240 joules. Q sub C, it says it is rejecting 100 joules to the environment. So that's Q sub C. And it says the temperature of the environment is 15 degrees Celsius. We're going to need that in Kelvin. So add 273, we have 288 Kelvin. And we want to know what is work, what is efficiency, what is T sub H. Well, I'll use conservation of energy, that work is Q sub H minus Q sub C. So 240 minus 100, and that's 140 joules. Efficiency is 1 minus Q sub C over Q sub H. So 1 minus 100 over 240. And we get 0.583, or we could say 58.3% efficient. And finally, T sub H is, well, using the Carnot efficiency equation, but solving it for T sub H. And I haven't shown you that algebra, but hopefully you can take it from the original equation to this for T sub H. It's T sub C over 1 minus E. So 288 Kelvin over 1 minus 0.583 repeating, which is the efficiency, and we get 691 Kelvin. Now, since the information in the question was provided in Celsius, we should convert back to Celsius, so 418 degrees Celsius. Let's look at a quick little problem in the back of the chapter. Problem number 12 says a cosmic heat engine, so a little bit science fiction here maybe, might operate between the sun's 5800 Kelvin surface and the 2.7 Kelvin temperature of intergalactic space. What would be the maximum efficiency? So we certainly don't have a contraption like this built, but this is just an example of how efficient could we get it if we have a huge difference in temperature as provided in nature in outer space. How efficient could this engine be? And you see T sub H, you see T sub C for hot and cold. So efficiency, 1 minus T sub C over T sub H, 0.9995 or 99.95%. And that would be a very efficient machine. As opposed to, you can see in the previous example, which is more likely more realistic. In example 19.1 at the top of the page, we got a 58.3% efficient machine. Let's look at problem number 32. It says a Carnot engine extracts 745 joules from a 592 Kelvin reservoir during each cycle and rejects 458 joules to a cooler reservoir. All right, so right off the bat, I've written down Q sub H, extracted, temperature, 592 Kelvin, temperature sub H, and Q sub C, which it rejects into a cooler reservoir. And it does that for each cycle. Then it says it operates at 18.6 cycles per second. Okay, so that's giving us some information about the timing. So I'll just write that off to the side, 18.6 cycles per second. And it asks, what is the work done during each cycle? What is its efficiency? What is the temperature of the cool reservoir? And D, its mechanical power output. So mechanical power, remember power involves energy per time. So it's in that fourth question that we're going to need to figure out. About what this 18.6 cycles per second means. So for the first question, what is the work? Conservation of energy says work is Q sub H minus Q sub C, and we get 287 joules. The power output, well, now that we know we're getting 287 joules per cycle, but power is joules per second. So let's convert that. We have joules per cycle, and we know it's 18.6 cycles per second. And so the cycles will divide out those units, and we're left with joules per second. So we get 5338 joules per second, but I'll round that to 5340 watts. The efficiency is 1 minus Q sub C over Q sub H, which is 0.385. We could also have gotten efficiency as work divided by Q sub H. And that also, of course, gives 0.385. And finally, the temperature, the cold temperature. We're going to use the Carnot, the efficiency equation, and solve it for T sub C. So that's T sub H times 1 minus E, and we get 364 Kelvin. Now in section 19.3, we're going to look at some applications of the second law. And I want to talk about refrigerators, air conditioners, and heat pumps. Thermodynamically, refrigerators, air conditioners, and heat pumps all do the same thing. They are heat engines in reverse, and their purpose is to defy nature. Here's what I mean by that. You think about an air conditioner. Imagine it's a hot summer day, it's 100 degrees outside, and it's 80 degrees inside the house. Nature wants to bring the heat from the high temperature outdoors to the lower temperature indoors. That's what spontaneously happens. Heat always goes from high temperature to low temperature. But the purpose of an air conditioner is to make heat go in the reverse direction, from the cool temperature indoors to the hotter temperature outdoors. So an air conditioner will extract heat from the outside and from the inside and dump it on the outside. Now, in the process, work must be done. We can't simply take heat from the interior of a house or the interior of a refrigerator and dump it to the outside of the house when it's warmer, or the outside of the refrigerator. But if we have a motor that's running, it can aid in that extraction of heat. So let's talk about these. Let's look at a refrigerator, and you see to the left my schematic of a heat engine, just as I drew it on the previous page, and now compare it with the schematic of a refrigerator. It looks pretty much the same, but notice the flow of the heat and what the different reservoirs are. So with a refrigerator, you've got a cold inside of the refrigerator. The purpose of the refrigerator is to extract heat from the cold inside and dump it into the kitchen where it's warmer. Now, if the refrigerator isn't plugged in and it's not working, heat will naturally go from the warm kitchen into the refrigerator, but we want to do the reverse of that. Well, in order to take heat and make it go in the direction that defies nature, we need a motor that does work. So heat is extracted from the low temperature reservoir, in this case the interior of the refrigerator. And to do that, work is done by a motor. Together, the joules that are extracted from the interior of the refrigerator and the joules of work done by the motor, together by conservation of energy, they make the total amount of heat that is dumped to the outside of the refrigerator into the kitchen where it's a higher temperature. Conservation of energy here says that W plus Q sub C equals Q sub H. This is a picture from the cartoon The Simpsons. On a summer day, Homer got an idea that while their air conditioner was broken or wasn't working very well, he noticed that it's cold in the refrigerator. So he set up a tent, and what he wanted to do was enjoy the cold of the refrigerator to live in the tent. But the problem is that the refrigerator, in drawing heat from the inside of the refrigerator, which now has become the tent effectively is part of the inside of the refrigerator, so it draws heat out of the tent. A motor is running, that's energy produced given by electricity from the wall outlet, and all of that heat, together the heat that is drawn from the tent and the extra energy added from the electricity, all gets dumped out the bottom of the refrigerator back into the tent. So actually there's more heat, there's a higher temperature, more heat is pumped into the tent than was extracted. So now the refrigerator is working on overdrive to extract that heat, but then the motor's running, there's those extra joules of energy, and it dumps the heat back into the tent. So this is a very, very bad idea, and in fact, it would only get hotter inside that tent. Now, when we talk about a refrigerator, how well it works, we want to think about the efficiency. However, we're going to use a slightly different term because efficiency is always a ratio between 0 and 1. However, the concept of efficiency is still there, but we're going to use a slightly different term called the coefficient of performance. And it's still the idea of efficiency that it's a fraction, it's a ratio of what you want divided by what you supply or what you pay for. Now for a refrigerator, the coefficient of performance, you think, what do you want? You want heat extracted. You want a lot of joules of heat extracted from the inside of the refrigerator. That's Q sub C. What are you supplying to get that? What's the cost? Well, it's W. You have to get that motor running. So the coefficient of performance is Q sub C divided by W. And again, the reason we don't call this efficiency is that efficiency is always a ratio between 0 and 1. And in this case, it's going to be something more than 1. And conservation of energy says another way of looking at it is Q sub C over Q sub H minus Q sub C. Now, an air conditioner is very similar to a refrigerator. However, the difference in the diagram that I've just drawn here is with an air conditioner, instead of the cool or the low temperature region being the inside of a refrigerator, now it's the inside of the building, the inside of the house, the cool interior of the house. And the heat is going to be dumped outside into the hot summer air. But the flow chart, the schematic here, is exactly the same as for a refrigerator. So the coefficient of performance for an air conditioner is what you want, which is Q sub C, heat extracted from the building, and what you pay for is what you supply is the work done by the motor. You pay for the electricity. You need to supply that electricity to get the motor running. So just like for a refrigerator, coefficient of performance is Q sub C over Q sub H minus Q sub C. Now, I want to look at two things. One thing is a window air conditioner, and the second thing is the question. Actually, I want to look at this question first. Does a fan cool the room? So you've got a warm room, you plug in a fan, and it makes you feel cooler. But I want to think about the question, does a fan really cool the room? I want you to see my little picture there. It's plugged in, meaning it's drawing electricity. So you're actually adding energy to the room. And the fan blade spins, you're adding kinetic energy to the air. And if anything, a fan actually warms a room up. Now, it might be an imperceptible change in temperature, but a fan definitely does not cool the temperature down of a room. So why do we use fans? Well, a fan only has a cooling effect if there's someone there to enjoy it. And it's kind of like the philosophical question: if a tree falls in the forest and nobody's there to hear it, did it make a sound? Well, a fan doesn't work unless somebody is there to enjoy its cooling effect. Because what a fan does is it blows the air, the warm air, away from your body. It also helps in the evaporation of perspiration, and these are things that cool off the body. So yes, you feel a cooling effect when that air is blown over you. But if nobody's in the room, turn the fan off, because most likely, most likely you're just adding energy to the room. Let's look at a window air conditioner. Emphasis on the window air conditioner. In order for an air conditioner to work, it extracts heat from the interior, from the room. But remember the schematic, the flow chart I drew for you, it has to dump the heat into a higher temperature area. So we put them in windows. Now, more sophisticated air conditioners are ventilated, so they're not sitting in the window, but they're ventilated somewhere. It has to dump the heat to the outdoors or just away from where you want to cool in order for it to work. So a window air conditioner by itself will not cool off the room. If you just have a window air conditioner sitting in the middle of a room, yes, it will extract heat from one side, but it's going to dump even more heat out the other side because it's got the heat it extracted from the front, but then there was energy from the work done by the motor. It's going to dump even more heat out the back. So here we have a window air conditioner, and there we have looks like a technician working on the outside. That's where it blows the heat. Here we have somebody has rigged up a van, and this van has an air conditioner in it, and this should work pretty well. So the idea is that it's going to take the heat from the inside of the van and dump it out the side, dump it to the outdoors, and that could work. So remember, with a ceiling fan, it doesn't cool down the room itself, or any fan. It doesn't cool down the room itself, but rather it actually adds energy. But the blowing of the air gives our bodies a cooling effect. I talked about a refrigerator and then an air conditioner. The top of the page is just what I've already covered. Let's look at a heat pump. Here's the schematic. It looks very familiar. It's the same as an engine and an air conditioner and a refrigerator, but let's look at where the heat is going. Think about the purpose of a heat pump. It is a cold day outside, and it's warmer inside the house, and nature wants to take the warmth in the house and bring it to the outside. That's why on a cold winter day, we don't want to leave the windows and doors open, because the heat will go outside. In fact, what we want to do is take heat from the outside and pump it into our already warmer house. So here's a heat pump, or thermodynamically, here's what it looks like. We've got the outdoors, which is a colder temperature, and we want to take the heat from outside and we want to dump that heat into the warm interior of the house. But in order to do it, we have to do mechanical work. Coefficient of performance, again, is what you want over what you supply. So in this case, we want Q sub H. We want joules of energy pumped into the high temperature reservoir, the inside of the house, divided by the work done by the motor. So coefficient of performance is Q sub H over W. Or by conservation of energy, we could say Q sub H over Q sub H minus Q sub C. We'll do problem number 16 in the back of the chapter. It says, how much work does a refrigerator with a coefficient of performance equal to 4.2 require to freeze 670 grams of water already at its freezing point? I've written down the given information. COP is 4.2. There's no units to that because it's a ratio of joules divided by joules. We want to know, what is the work? How much work does it do to freeze 670 grams of water at 0 degrees Celsius? Well, let's figure out how much heat needs to be extracted. So in this case with the refrigerator, we need to extract that much heat from the water, and it's going to take that heat and dump it to the outside of the kitchen. So remember that when we're talking about freezing water, Q sub C is M times the latent heat of fusion. Now I taught you when we did this chapter, an earlier chapter, to make that negative. But in this case, we're really concerned with how much is being extracted. So we're going to keep it positive. We're going to keep the absolute value. And so we'll do mass times L sub F. There's the mass, the heat of fusion of water. You can look that up in chapter 17 in a table there. 334 kilojoules per kilogram, or 334 times 10 to the third joules per kilogram. And what we get is Q sub C is 223,780 joules. Now, the coefficient of performance is what you want over what you supply. So Q sub C over W. We want to solve for W. It's Q sub C over coefficient of performance, and we get 53,280 joules. So in order to extract those 223,780 joules of heat from the water, the motor needs to do 53,280 joules of work. And I've written here in blue a way of thinking about coefficient of performance of 4.2. It means that for one unit of work times 4.2 means for every unit of work, you can think every joule of work, you need to do 4.2 units or joules of heat that's transferred. And a higher coefficient of performance is more efficient. Now, just as when thinking about an engine, we had an ideal engine or a Carnot engine, we can also think of an ideal refrigerator or an ideal heat pump. And it's the same concept as with a Carnot engine. And mathematically, we can do the same little trick, switching out the Q's and T's. And we get this. The maximum coefficient of performance for a refrigerator is the cold temperature, or the temperature of the cold reservoir, basically inside the refrigerator, divided by T sub H minus T sub C. This is the maximum possible coefficient of performance that a refrigerator can have, or an air conditioner can have. And it's determined by just two things: the different temperatures. Temperature on the outside and the temperature on the inside. And keep in mind, for this to work, you need to do it in Kelvin. For a heat pump, the coefficient of performance, I already showed you, is Q sub H over Q sub H minus Q sub C, but the maximum possible coefficient of performance is, turn those Q's into T's. So the high temperature divided by the high temperature minus the cold temperature. So when you make those temperatures a wider difference, or a narrower difference, that's going to affect your coefficient of performance. Let's look at problem number 15 in the back of the chapter. It says, find the coefficient of performance of a reversible refrigerator operating between 0 degrees Celsius and 30 degrees Celsius. And we're just going to gloss over that word reversible. It basically means a perfect refrigerator where the best coefficient of performance is possible. The book goes into more detail about what exactly reversible processes mean, but it's enough to know here that we're talking about the best possible coefficient of performance. We need the temperatures in Kelvin, so that cold temperature, it says in the problem 0 degrees Celsius, we'll say 273 Kelvin. The hot temperature, so the kitchen is 30 degrees Celsius. We'll make that 303 Kelvin. So the best possible coefficient of performance is T sub C over TH minus TC. Plug those values in, we get 9.10. Let's look at example 19.3 in the book. It says a typical home freezer operates between a low temperature of 0 degrees Fahrenheit, and here it's done the conversion for us, 255 Kelvin, and a high of 86 degrees Fahrenheit, and it's done the conversion, 303 Kelvin. What's its maximum possible coefficient of performance? Okay, so we just solved a problem like that on the previous page. But now with this COP, how much electrical energy would it take to freeze 500 grams of water initially at 0 degrees Celsius? Okay, so we can find the COP, which is T cold divided by T hot minus T cold. Use those Kelvin temperatures. You can't use Fahrenheit, can't even use Celsius. They have to be Kelvin, and we get 5.31. And now we can find the heat that needs to be removed in freezing 500 grams of ice. So Q sub C, that's the heat extracted, is the latent heat of fusion. Now in the book here, right below where my red pointer is, it doesn't use L sub F, it's just saying L, but we need to be talking about the heat of fusion times the mass. So 334,000 joules per kilogram times 0.50 kilograms, and we get 167,000 joules, or 167 kilojoules. It says the COP is the ratio of the heat removed to the work or electrical energy required. So we have work is Q sub C over COP. So Q sub C, 167 kilojoules divided by that coefficient of performance, 5.31, and we get 31 kilojoules. That is the end of sections 1, 2, and 3 in chapter 19. Have a great day.